Hey, this is Hunter, and this is the 2019 set one, number three. This question is primarily about rotational inertia, conservation of angular momentum, all kinds of great things. So we'll take a look at it. To begin with, we have a horizontal circular platform. So there's our horizontal platform, has a rotational inertia of IP, rotates freely without friction on this vertical axis. We have a small motor-driven wheel, and you'll see that right here. It has a radius r, and it is a distance d from the platform. So right off the bat, we know that from the center of this platform over to where the wheel is touching it underneath, that is the radius of the platform, and that's equal to capital D. So this would be the radius of this little motor-driven wheel. So I'm going to put a little m on it because I think that'll help as you go through and take a look at it. So the platform starts at rest. So we know that the initial linear velocity is equal to 0, and the wheel exerts, and so we'll do the same thing with angular, that is also 0, and it exerts a constant horizontal force of magnitude F tangent to the wheel until the platform reaches this angular speed at a time of this. So now we've got that. During this time, the wheel stays in contact and there is no slipping, which is good. They want us to go through and derive an expression for the angular speed of the platform and express all of our answers in terms of IP, RD, F, delta T, and physical constants as appropriate. So we know that this is creating a torque on this wheel. So we're going to just say that torque is equal to the moment of inertia times alpha. And for this one, we know that we have a force times a distance. So it is the force from this wheel acting on this distance. And notice that these are at 90 degrees, so there's no trig function that we need here. And that's equal to IP, so that's the moment of inertia of the platform, times its angular acceleration. So now we've got angular acceleration is equal to FD all over IP. And we don't want to solve for alpha. They want us to solve for omega p. So this is where they're trying to get you to do some kinematics. We know that the final angular speed is equal to the original angular speed plus alpha times delta t. And we know that this is 0, so we're not going to worry about it at all. And we know that alpha is FD over IP. So we'll rewrite this. And so we've got the final angular frequency is equal to the FD. Now FD came from alpha. And we have to multiply that times delta t. And then we're going to divide that by IP. So this is IP. Now we have the correct stuff. So where do we get points? We get 1 point for doing this side, and we get 1 point for doing this side. So now you've got your 2 points for that part. Letter B wants us to determine a equation for the kinetic energy. So just one derivation right after the other. This is kind of the new way of doing AP Physics C. So I know that this kinetic energy is rotational kinetic energy, so that's 1/2 I omega for that platform squared. And we just derived the equation for the final angular speed of the platform, so we can plug it in. So this is equal to 1/2 of I times, and now we've got the force times distance times delta t all over I, and we're going to square that. The next part that, or the next thing that we need to do here is solve for k, and if we solve for k, here we've got 1/2. Now be careful, the temptation here is to cross off both i's, but notice this is squared, so you really can't do that. So I've got 1/2 of, and then I've got FD delta t, and that is squared over I. Notice that the 2 and the I are on the same spot, so now we can just change this and say FD delta t, and that whole thing squared. If you don't put the parentheses, then this is not correct, and that's over 2I. So to do this, you'd have to show the equation for rotational kinetic energy, And then as long as, if you mess this up, but if you plug it in down here, right here, you're going to get this other point. So even if you did this wrong, as long as you have this very equation, and then you plug in for your final angular speed, whatever it is that you have here, even if it's not right, they'll give you both points for that. So really important to kind of follow through with what you've got. Next thing they want us to do is derive an equation for the angular speed of the wheel when the platform has reached an angular speed of omega p. So they want us to express our answer in terms of dr, omega p and physical constants, as appropriate. So for this one, we know that the velocity, okay, of that platform is equal to the velocity of the wheel, or we could say we have r times omega, and that is for the platform, is equal to r times omega, and that is for that little wheel. Okay, so be really careful that you're seeing what these are. This is for that little motorized wheel. And so if we go back up, that's for this motor-driven wheel. And so they're using omega W for it. Okay, so now that we have that, let's go ahead and plug in things that we already know. Since we have to use these things, we want to be really careful. So for the platform, we don't call the radius r, because now we would have the same r, so we call that d. So we need to substitute that in, and then that's times p, the omega p. And then this is just the same thing as it was, so r times omega w. Now we need to solve this for omega w, so we get our points, because if you don't solve for it, they won't give it to you sometimes. And now we have solved for it, and we are done. So far, really super simple problem. I think the big thing here is you got to have this. Probably you won't do that. You really should do this, since we're looking at the rotational stuff. Then you get one more point for doing these two steps. If you don't show all three of these, you probably will not get credit, because you have to kind of show where this r turns into d, and it's not real clear when you do it over here. I mean, you and I think it is, but the College Board sometimes has a different way of thinking about it. Next part that happens, the platform is spinning at an angular speed, and the motor-driven wheel is removed. So we got rid of that guy. Student holds a disc directly above and concentric with the platform. All that means is that this fits right on top of this, and there's nothing that is going to overlap unevenly. Otherwise, that whole thing would wobble really bad, and we don't want the wobble. So student holds it, and the disc has the same rotational inertia as the platform, so these two are the same. They release the disc from rest, and the disc falls onto the platform. So immediately your brain should go, aha, there is a lab that we have done or will do in AP Physics C, where we're conserving angular momentum. So when you drop these on, we're going to double the mass, which means that our angular momentum will be conserved, but that means that our final speed should be less. So the student releases the disc from rest, and it falls on the platform. After a short time, the disc and platform are observed to be rotating together with an angular speed of omega f. And so here is what we want to do for this part. We need to show that there is an angular momentum before and there is an angular momentum after, and that the equation for each one is I1 omega 1 is equal to I2 omega 2. Now that we've done that, we need to substitute in for our speeds, well, for our, what's going on? So we have, still have I omega for the platform, okay? But now we have a new I, and the new I is just double of what we had before. So that would be not 2I2, can't put that, but instead 2I for that original angular moment, angular or rotational inertia, and then that's times omega final. So when we look at this, we notice that we have I here also, and so we can cross those i's off, and we're left with WP is equal to 2WF, but they want this for omega F. So omega F is going to be 1/2 of the angular speed of that platform when it was just spinning all on its own. So you get 1 point for really showing, oops, let's do this in red. You get 1 point for showing this part where we're seeing how the angular momentum is conserved. And then we get 1 point for showing these two steps where you're substituting in. We're saying that we've doubled the moment of inertia because we've doubled the mass. And then you have to cross off the i's, and we put the omega final is equal to 1/2 omega p for the platform. Next part, student now goes through and they take that rotating platform, which has a IP of 3.1 kilograms times a meter per second. Meter squared, to determine the rotational inertia IU of an unknown object. And that vertical axis passes through the center of mass, which is good. The platform is rotating with an initial angular speed of omega I, when the unknown object is dropped on the center. And when it does that, the platform and the object spin at omega F. Trials were repeated, and then we have different values of the speed. So as we increase the speed, we see that there's a linear relationship here. So next thing, we have to draw a straight line. So this, you'll definitely want to use a ruler. So ruler for sure. And I don't think I have a line tool. And so, yes, I do. So what I'm going to do is I'm going to use my line tool to do a best fit through the dots. Notice that all the dots pretty much are here. We don't have anything that's kind of way out on the sides. If we did, we could ignore that. And so we want to try to get the same number of dots on top and below the line. We do know that if we think about this, can we have a 0 omega I? And yes, we could have a 0 omega I or F. And so we really can, if we want to, start at 0. And then we want to go through and try to have the same number of points on the top as we do on the bottom. We have 5 points, so that makes it a little bit harder. So what we're going to do is we're just going to place our line just like that. And now we have our line. So this is our best fit line. Having it go through 0 is really nice, because then that way, for us to calculate the rotational inertia, we just have to try to figure out what is the, we've got to go through and kind of do the slope of the line. So we're going to do that here in just a second. So we have drawn that best fit line, and that is 1 whopping point. But boy, that's a really easy point to get. So now that we've done that, they want us to go through, and on this part, we've got to figure out what is the moment of inertia, so IU. We need to start by saying that we know that the the angular momentum initial should be equal to the angular momentum final. And for this is IP omega initial, and that's equal to IP plus the moment of inertia of that unknown object, okay? And that is times omega F. So we just add the two moments together, and that will give us the final moment. Now we're going to substitute in and go ahead and solve this for IU. So IU is equal to IP times the ratio of omega I over omega F, and we're going to subtract IP. So we've just taken this equation and we've solved it for IU. We first had to multiply both IP and IU by WF. Once we did that, we could subtract, and then we could go through and do the ratios. So that's kind of what you'll see. Let's go ahead and substitute everything in now. So we said IP is 3.1 kilograms times a meter squared. And this is where you're going to have to really stop and pay attention. So stop, pay attention. Okay? Notice, this is omega I over omega F. Omega I is here, omega F is here. So you're not really going to find the slope, you're going to find the inverse of the slope. So whatever you do, please make sure that you always look to see what they've plotted. They love to do this. They're trying to trick you. There's just no way around it. So what we're going to do here is we are going to make sure that we kind of go through and be really careful with what we get. So this is omega I over omega F. Okay, so omega I over omega F. Alrighty, so I think the easiest thing to do is let's just pick this point right here, and then let's pick the origin since we have those two. So our omega I is going to be 4, so this is 4 minus 0, over, and then our change in omega F is going to be about 1.8 minus 0. And then we're going to subtract from that 3.1 again. So let's see what we get when we do that. 4 divided by 1.8 gives us 2.22 times 3.1, and then we're going to subtract 3.1. So we end up with 3.8. So 3.8 is our moment for this unknown object. So 3.8 kilograms times a meter squared. The key online is not right. So please, if you look at it, they're going to have 4 minus 1 over 9.3 minus 2.4, and that can't be correct. Because if you do that math, you're going to get a really funky answer. So the key is messed up. So please, 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 please be careful when you use the keys. Okay, so speaking of the key, let's figure out where we get points for this. We do get a point for showing this part of the work. So that would be this and this. For rearranging, plugging in the correct numbers, unlike what they did, you get another point. So there's the other one. Alrighty, the kinetic energy displaying platform before the object is dropped is Ki. The total kinetic energy when it reaches that final speed is Kf. They want to know which one of the expressions is true. And the correct answer for this one is the final kinetic energy is actually less than the original kinetic energy. Because both platforms have the same final angular speed. So therefore this is an elastic collision. I'm sorry, inelastic collision. It is an inelastic collision, and kinetic energy is lost during the collision. So because, C-O-L-L-I-S-I-O-N, because it is inelastic, we know that you have to lose kinetic energy. So you can fall back on what we did in energy to kind of help you. One of the students observes that the center of mass of the object is not actually aligned with the axis of the platform. So what that means is we've got the platform, so we're looking from the top down. And let's say that the object that we have gets dropped, but it gets dropped over here. It's an irregular object, and its center of mass is right there. The center of mass of the platform is right there. So now it's not in there. So if the experimental value of IU is obtained in part E, is it greater than, less than, or equal to the value of the rotational inertia of the unknown object about the vertical axis that passes through the center of mass? So if we would have had this fall, and it would have been right in the center, no matter what shape this guy is. So let's say that that is the center of mass of the object and that is the platform, then it's going to come out pretty evenly. But here, now that center of mass is further out, and we know that if we have this further out, we're going to have to think about the parallel axis theorem. So we know that the total moment of inertia is going to be equal to the moment of inertia of the central of the center mass of the disk, and then we have to add to that the center mass of this at the radius, so that would be mr squared. So that would be bad because it is off by a little bit. Therefore, we're going to say that it is greater than, and we actually can use what we have right here, and you'll see that now you can just say that the experimental value is off by mr squared. Or you could use mh squared, totally up to you. So where do we get points on this one? We get points for selecting greater than, and you get a point for explaining it. Same thing on this one, you do get a point for checking the right one and for explaining it. So altogether we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 points. And that is really a nice problem. Pretty simple, very straightforward, makes you think just a little bit with this, but other than that, no calculus at all. Just a really cool little problem.